Oh, hi. Welcome to part B of our lecture. This is chapter 3, part B. And today I do have three sections I would like to go over and wrap up chapter 3. What I like to do is usually share my screen so that you can take notes wherever I work or I solve a problem, go through examples. So let me share my screen and you should be able to see the lecture PowerPoint slides as well as the whiteboard. Uh, so far, we have gone as far as section 3.4, and today I want to start from 3.5, 3.6, and wrap up with 3.7. In 3.5, we will look at the empirical formulas and how to determine the molecular formulas. Dive into the quantitative information from the balanced equation. So far, we have looked at the concept of balancing the equation. Please practice on those. We will use the coefficient in the balanced equation to decipher information or get the information from a chemical reaction. And lastly, we will look at the limiting reactant and excess reagent. Wherever you are given a chemical reaction, you are given the reagents, reagent A and reagent B. It does not mean that all the reactants will be consumed at the same time or they will run out at the same time. There are some chemical reagents reaction which might consume both reactants at the same time, but that is not always true. Some reagent may be consumed before the other one run out. The one which runs out fast is called the limiting reagent. The one which will remain or which there will be a leftover of that reagent is the excess reagent. We look at how to determine the what? The limiting reactant, look at how to find the theoretical yield and percent yield of course from a chemical reaction. Um, as far as the definition of limiting, I mean empirical formula is simply the simplest, you can define this as the simplest whole number ratio of atoms of elements in compound, right? Generally, these are the subscript values you see on the chemical formula of a compound. That formula is basically the empirical formula. To understand, you don't see anything subscript for sodium, subscript for chlorine. However, there is one sodium, there is one chlorine. You don't see it here. This represent 1-to-1 ratio of atoms in sodium chloride, formula unit of sodium chloride. We call this empirical formula. Dinitrogen tetroxide, for example, this is not empirical formula because it's not in the simplest form. So let's see if we divide by 2 both sides. This means we have NO2. This is molecular formula, and this is what empirical formula. It's just to define what empirical formula is. There is a procedure by which you determine the empirical formula from analysis. You may be given the masses of what? Masses of elements in a compound, and you are asked what? To determine the empirical formula. You may be given either masses of elements. You will need to what? If given the masses of element in a compound, you need to convert into convert. One thing is convert into moles using using the molar mass of each. You get this molar mass from the periodic table, from molar masses or atomic mass using the periodic table for each element, and then you convert into moles of that element. And look at the simplest, divide both sides or across by the smallest number of moles. If you look at the worked example in the text and reconcile with this roadmap, it will walk you through on how to find the empirical formula. So if I'm given mass of each element, I'll use the, if I'm given the grams, forget about this first. If I'm given the grams of each element in a compound, use the molar mass. You would use this, use the periodic table to find the atomic mass or molar mass to get the moles of each element. And then you do what? You divide by the smallest to get the ratio. There you'll have the empirical formula. This part here, mass, sometimes you may be given the mass composition of an element. Just assume that you have 100 grams and convert that into the grams of element. It could be 70.30% carbon. Let me just give you what this percent means. You will take this as 70.30 grams of carbon, and then you convert to moles of gold. So assume you have 100 grams. Sometimes you may be given only, if you have 3 elements in a compound, 3 elements in a compound, and you are given percent of the 2, you will add the 2 and subtract from 100 to get the percent of the third one, which is the same as grams for that element. Let's see, if you are given the percent composition, just assume they are 100. There are 3 basic steps you will follow in determining the empirical formula for a compound. Here is an example, the compound para-aminobenzoic acid. You may have seen it labeled as Papa on the bottles of sunscreen, right? It's composed of 61.31% carbon. Hydrogen is 5.14%, nitrogen 10.2%. These represent grams, so forget about the percent. I'll say, all right, I'll say I have what here, 61.31 grams of carbon, and I have what 5.14 grams of hydrogen and 23.33 grams of oxygen. If these are the grams, what we need to do is convert to moles using the molar mass or atomic mass of each element. Using the 2 places of decimal, this is 12.01 grams of carbon, weigh or as equals to 1 mole of carbon. For hydrogen, 1.01 grams of hydrogen, 1 mole of what? Hydrogen. And lastly here, 16.00 grams of oxygen, 1 mole of oxygen. What this setup means is I'm converting the grams to moles, and I started with percent. So forget about the percent symbols, just assume you have 100. So if you are given only the first 2 elements, you can add that, subtract from 100 to get the third, to get the mass of the third element in a compound. This setup will, on the whiteboard, will give you the number of moles of each element. That's the starting, that is step number 1. So if we walk through that, you will see that the first setup is to change the grams of carbon to moles of carbon, grams of carbon to moles of carbon, hydrogen grams of hydrogen, we add percent, so that's going to be the number of moles. And lastly, nitrogen. Was it nitrogen? Let's see. I think it was nitrogen. Let's assume nitrogen. I think there's a confusion here, but nevertheless, if you look at the setup we use here, nitrogen. So if we use nitrogen, that will change. Nevertheless, the setup is the same. Okay. So don't forget to use the correct atomic mass. So if we say nitrogen, change this to nitrogen in the PowerPoint slide, change here to nitrogen, and it will conform with the setup here. So if I look at the number of moles, if you look at the number of moles here, 5.105, 5.09, and 0.77. Once you get here, you divide by. It's important to do this. Divide all by the smallest, smallest number of moles. So you have to look at which one. Doesn't really matter where you are starting. Let's say nitrogen was number one here or at the top, or it was in the middle here. We'll just have to eyeball and see which one is the smallest. This is the smallest, so that means we'll divide across by 0.7288. 288. Oh, we have oxygen. Okay, we had nitrogen again, so that's going to be nitrogen. We had nitrogen here, so we will have to use oxygen. This will actually give us the empirical formula C7. If you look at the empirical formula C7N2, these are the simplest whole number ratio for that compound, simplest whole number ratio of compound. So remember, we had nitrogen in the compound, all right? We add nitrogen and oxygen. I forgot to put nitrogen here or oxygen. So this will be for nitrogen is 10.21 grams of nitrogen, and oxygen is 23.33 grams of oxygen. This is 14.01 times 16.00. This is 1 mole of oxygen. So that's the setup. And then you divide by the smallest number of moles. That will give you the what? The simplest whole number ratio, C7H7N1, because nitrogen was the smallest, and oxygen. Please don't round off. I know sometimes we may be tempted. Let's say, for example, you have, I'm just going to give you a generic formula. Let's say you have A and you have to be 1.5 and B there, it is 1. Do not round off 1.5 to our whole number and say that it is going to be A to be like that. This is wrong. What you need to do is multiply both sides by 2, multiply both sides by 2, and this will give you A3 B2. All right. You may wonder, why should I use 2, or what is the criteria by which I pick 2 to multiply by the number of moles across. When you have a fraction, what I mean by a fraction is the decimal point. In this case, it is in 1.5, I have 0.5. So what means is, I'll say 1 over 0.5, this will give me 2. So I'll multiply across by 2. If I have, let's say, 1 0.7, for example, I have 0.7, so it's going to be 0.7, 1 over 0.7, and it's going to give you a value. So if I have a calculator, all right, if I use my calculator here, 1 divided by 0.7, it's giving me 1.4. So this means I'll multiply across by 1.4, okay? I'll multiply across by 1.4. So if it was A 1.7 and B 2, for example, I'll multiply here by 1.4. I'll multiply here by 1.4. And then at this point, you can round off, But for most part, it will just be what? It will just be a whole number. It will just be a whole number. I will post more problems on Canva so that you can practice, watch YouTube, more YouTube recording on how to determine the empirical formula, use end of chapter problems, following the step I've outlined on determining the empirical formula. I'll solve one more at the end, but first let's see the molecular formula. Molecular formula, MF, is a multiple of empirical formula, EF for empirical formula. Remember, molecular formula shows the actual number of moles, or I mean actual number of atoms in a molecule. Actual. This is empirical formula. Before we look at that, before we look at how to use this equation to find the empirical formula, I mean molecular formula, we have a compound such as benzene, for example. Here is the molecular formula, and its empirical formula is CH. This is empirical formula. If you look at this, that means we have CH, and we are multiplying it by 6. This N is an integer, 1, 2, 3. All right, it can be any whole number. N can be any whole number. This is given by N is given by the molecular weight or molecular mass. This can be mass of empirical formula, mass, empirical formula mass. This is just the molar mass of empirical empirical formula. So the lower part, the denominator, is simply the empirical formula, the molar mass of empirical formula. The molar mass of empirical formula. The top part, this one is always, you will be given, for most part, always given in the problem. The top part you will be given, but the lower part you will be, you will have to determine from the empirical formula. So the multiple you see here, all right, a multiple of a number of atoms in the empirical formula is simply the molecular empirical formula. We multiply by an integer to get what? Molecular formula. We can find the empirical formula. You may be asked in part A of the question to find the empirical formula. You'll be given the molar mass, the molecular weight of that compound. And then we'll have to proceed with that. Let's see, the empirical formula of a compound was found to be CH. So if that is the empirical formula of a compound, we know the empirical formula, okay? It has a molar mass. What is the molecular formula? What is the molecular formula? So we know this is right here. This is the molar mass, which will be always given at the top. If I'm given the empirical formula, I can find the molar mass of empirical formula. So for that, if this is the empirical formula, means empirical formula mass is given by 12.01 to 2 places of decimal. This is the atomic mass of carbon. Hydrogen is 1.01 grams and 20 grams. This is 13.02 grams. This is the molar mass. And by the way, it is per mole. Units for that is per mole. So if we want to find our N, we use this equation. So it's going to be 78. All right. N equals to 78 grams per mole over 13.02 grams per mole. Grams per mole will cancel out, grams per mole will cancel out, all right? If we cancel out this to be precise or exact, 78 divided by 13.02, all right, 13.02, and I see is 5.9907. To make it a whole number, this is about 6. So if I have the N value now, that's the N, you cannot leave it in this state or just say and say I have the molecular formula. You need to do it to multiply by N, and this is the correct empirical, molecular formula for this compound. So at times you may be asked to find or determine the empirical formula in part A of the problem. Once you get the empirical formula, you'll be given the molar mass of the compound, and you are asked to do it to find the molecular formula for the compound. So that's what we need to do. The reason why we are doing this is to find the empirical formula mass, this addition here. The other is using our own number. Please use all the digits on the periodic table. I'll give you the periodic table in the exam. Okay, in the quiz, you'll be given the periodic table. This is what I did on my whiteboard to get the empirical formula mass. So the equation on, or this calculation here, is to find the whole number N, molecular formula or molar mass at the top, divided by the empirical formula mass, And once you open that, that's what I was talking about here, that you cannot just leave it in this state, but you need to open it. That's why this number is multiplied by the empirical formula. This, you have the molecular formula. It's as easy as that. It cannot be more complicated than just finding the empirical formula if you are not given, and you may be asked to find the molecular formula. Remember, previously given the percentages of elements, you'll have to assume you have 100 grams of what? 100 grams of the compound, and proceed with determination of the empirical formula, find the molecular formula of the compound. Let's see, sometimes there are some problems relating to combustion analysis. When we talk about combustion, that means burning, right? And the specific, right here, combustion analysis, we are focusing on a hydrocarbon. You know what we mean by hydrocarbon? For most part, you'll be given combustion of hydrocarbon, which means they contain what? Carbon and hydrogen. Compounds which contain carbon and hydrogen are called hydrocarbons. This means the combustion of hydrocarbon will produce combustion right here. Hydrocarbon produce what? Produce two things. One, H2O and what? CO2. So those are the two products from the combustion of hydrocarbon, compounds containing carbon and and sometimes you may have oxygen here, may have oxygen or sometimes nitrogen. They will be specified. We'll analyze that and see, use it to do what? To determine the empirical formula of compound from combustion. So this one, the H2O will be used to find the number of moles of hydrogen. CO2 will be used to find the number of moles of carbon. And of course, if the masses of hydrogen and carbon does not add up to the mass of the hydrocarbon, that means the remaining mass is for oxygen. So what I'll do to find the mass of oxygen is sum up the masses of what? Hydrogen and carbon, subtract from the mass of the sample. You're given that. So what we will see here or take home from this slide here is understand that hydrocarbon has three things, and from its combustion, it produces CO2 and what? And H2O. Those are the two compounds we will use to find the empirical formula of what? The empirical formula for compound, okay? Masses of oxygen in the compound cannot be determined from CO2, but because oxygen is added during the combustion. So how are we going to find the mass of oxygen? We know for carbon and hydrogen, we can subtract from the mass of what? Mass of, here, I like this, mass of oxygen, all right? Mass of oxygen is determined from what? Original, say, original mass minus the sum mass of hydrogen plus mass of carbon. This will give you the mass of oxygen. And then from there, you change to what? You change to moles of each element using the atomic mass of the periodic table. You divide by the smallest number of moles, just the way we did before, to find the empirical formula. So here is the roadmap for finding the mass of carbon. First, you start with the mass of carbon dioxide captured, all right? This is how carbon dioxide is captured from the combustion chamber. This is how H2O is captured and determine its mass, determine mass of CO2. And if you see, or if you know the mass of CO2 produced, we convert to the number of moles of CO2 produced. Now, here is the mole ratio. If you look at CO2, for every 1 mole of carbon, we have 2 moles of oxygen. For every 1 carbon atoms, we have 2. So mole ratio, and then the number of moles using the molar mass in the original sample. We will see that when we get to the example. This applies to H2O. This is for determining the mass of hydrogen. Hydrogen is obtained from H2O. So this is how you walk through on how to find the mass of hydrogen in the sample. So if I know, look, if I know from the mass of H2O, mass of hydrogen, it's gonna be x grams of H2O times the molar mass of what? H2O, 1 mole of what? H2O. And then here, this is H2O. For every 1 mole of H2O, we have 2 atoms of what? Hydrogens. So that you reconcile that times for every 1 mole or atom of what? Atom of 1 mole of not H2O, but hydrogen, there is 18, not 18, but 1 grams of 1.0, 1 gram of hydrogen. So here you have to know how to, for example, here, look at 18. If you don't know how to set it up the way I do have it here, so that you know where you are heading, it will be difficult for you to end up with the correct mass. The last or the conversion here, this is the mole ratio between hydrogen and oxygen. Hydrogen and oxygen. I want to solve one example on combustion analysis, all right? I want to solve one example on combustion analysis so that you have an idea of how to use the combustion analysis to find the empirical formula for compound. So here, let's say carbonic acid. I'm just gonna make up an example here. Carbonic acid. Responsible for bad odor in socks, right? Some people might have that. Is composed of, all right? CHO. So those are the compounds in carbonic acid. We have what? Carbon, hydrogen, and oxygen. Here is the question, combustion. Look at this, combustion of 0.225 grams of acid, all right, produce 0.512 grams of H2O. No, CO2, this is CO2, not H2O, this is CO2, and 0.209 grams of H2O. What is the empirical formula? All right, the question is, A, what is the empirical what? Formula. All right, and then B, caproic acid. As a molar mass, has molar mass of 6 grams per mole. What is the molecular formula? What is the molecular formula. What is the molecular formula of the caproic acid? So those are the two questions, all right? Here is the question. Caproic acid is responsible for the bad smell in salts. It's composed of carbon, hydrogen, and oxygen. So how are we going to determine the empirical formula and molecular formula? This is combustion analysis. I know when you look at the numbers, if we are starting with these grams of the compound, and then we see another number which is even greater than what we started, you may wonder, how comes that we have a smaller or less mass, and then we produce more mass, yet we know matter cannot be created or destroyed. We need to do the combustion analysis in order to find the mass of carbon, mass of hydrogen, and mass of oxygen, mass of oxygen. So what you need to do is, this is how you will proceed. Let's say mass of carbon, mass of carbon. This is how you'll find the mass of carbon. We have 0.512 grams of carbon. Using the molar mass of carbon as a conversion factor, grams of carbon, we want to find the moles of what? So carbon. Carbon dioxide, this is CO2, sorry, CO2, and this will change to 44. 44.02 grams of carbon. So this will cancel, that will cancel. Up to that point, we have moles of carbon dioxide. We want to know how many moles of carbon. From the mole ratio, for every 1 mole of CO2, we have 1 mole of what? 1 mole of carbon. So that moles of CO2 will go with moles of CO2, which how I'm setting up my conversion factors. It cancels out. After that point, I'll only end up with the number of moles of carbon when 0.51 grams of carbon are produced from the combustion of the hydrocarbon. The last one here is we want to know the mass of carbon, which from the conversion factor derived from that atomic mass of carbon. We want the grams of carbon, 1 mole of carbon. So that moles and moles will go away. And what I have here is 0.14 grams of carbon. This is the mass of carbon in the hydrocarbon in the sample. What this means in this sample right here, in this sample given here, what I have is 0.14 grams of carbon. For mass of, look at this, mass of hydrogen, we are done with the mass of carbon. The mass of carbon. We want to know the mass of what? Hydrogen. In the same way, we know the mass of H2O produced 0.9 grams of H2O using the mass of H2O as a conversion factor, 0.2 grams of H2O. This is 1 mole of H2O. Cancel grams of H2O, grams of H2O. We have moles of H2O. The ratio here is from the atoms mole ratio of atoms of hydrogens to 1 mole of H2O. So for 1 mole of what? 1 mole of H2O, there are 2 moles of hydrogen. You see, when I write this, for every 1 mole of H2O, there are 2 of hydrogen, 2 hydrogen. So here is where the 2 is coming. You need to understand that it's going to be the same thing throughout. okay? So that when I cancel moles and moles, that will give me with the number of moles of hydrogen. You need to find the mass. So here is the conversion factor for every 1 mole of hydrogen. Is hydrogen, not hydrogen gas. You have 1.01 grams of hydrogen. So that moles and moles will cancel. You can multiply everything at the top divided by everything at the bottom. At this point, it is your responsibility to learn, master your calculator. You need to know how your calculator works. This is the grams of hydrogen in the hydrocarbon, number of hydrogen in hydrocarbon. So that's how you will determine the mass of hydrogen one from the combustion of hydrocarbon. Lastly, since we cannot use this method or this dimensional analysis approach to find the number of grams of oxygen, we have to use the packed channel to determine the mass of oxygen. Therefore, mass of oxygen right here, okay, will be the original, look at this original mass minus mass of carbon plus mass of what? Mass of hydrogen. Mass of carbon minus mass of hydrogen. This is what you will need to know on determining the mass of oxygen. So this is the original mass, all right? This is the original mass of the sample, 225 minus 0.0234 plus 0.140. This will leave you with 0.061 6 grams of oxygen. This is the mass of oxygen in what? In hydrocarbon. So we know now the what? We know now the mass of each element in the compound. So what we need to do is find the number of atoms for each element, number of moles of each element. So if I want to find for number of moles of carbon, is given by 0.140 grams of carbon times. This is the atomic mass of carbon, 1 mole of what? Carbon. Then I do the same thing for hydrogen, 0.0234 grams of hydrogen times what? This is the atomic mass of hydrogen, grams of hydrogen. So that and that, this is carbon here. Cancel that, cancel that. And then oxygen is 0.0616 grams of oxygen times 0. Not 0, but 16. This is 16. So this will give me the number of moles of what? Number of moles of each element. So here, the first one is 0.0117. Please check from your calculator. I got here 0.0232. This is 32. And lastly, 0.00385. That is 0.0385. So if I look at this, is the smallest right here. That is the smallest number of what? Number of moles. So I divide by itself. So here 0.00385. It's gonna cancel. This will be 1. If I divide here 0.00385, all right, this will cancel, leaving me with 6. This will be 6 here. And then divide here by 0.00385. And we are left here with 3. So these are the numbers here, 3, 6, and 1. So if I'm to write the empirical formula, this will be C3, H6, O, like that. All right. So once you know the empirical, this is now the empirical formula for carboic acid. We know the empirical formula. Next is to find the molecular formula, which is given by empirical formula times an integer, which we know, or we can find n. This is n. All right, this is n. Here, look. N equals to molar mass or molecular weight. Sometimes the word weight is used of empirical formula mass. The denominator is simply the molar mass of empirical formula. So here, this is the empirical formula. Empirical formula mass, you have to use the periodic table, and stands out to be 58.09. Where I'm getting that is just using this formula here. This is the empirical formula of the compound. Use the periodic table to find what? To find the molar or molar mass, molecular weight of the empirical formula, which is the 58.09. And by the way, it is grams per mole, grams per mole. So we will plug it in this equation. And if I go back to the original, let's go back to the original question, and you see that you are given the molecular formula here. Next, carboic acid has a molar mass of, so we have a molar mass of 116 grams per mole. This is the molecular weight of that. The reason why we are given that is so that we find the what? The molecular weight. This is B. So here, N is 116 grams per mole over 58.09 grams per mole, grams per mole course, and N is 2, N is 2. So that empirical formula now here, molecular formula is given by C6H, C12, C3. I meant to say that this is C3. Did I miss that? 6, it is 1 there. So we have 2 there. Make sure I have that right. So that is what we had, empirical formula. That's the empirical formula. And when I plug it in here, the molecular formula is C6H12 and then O2. So our views or this example illustrate how to use the combustion analysis of an hydrocarbon to determine the empirical formula and molecular formula. I recommend that you do more examples on combustion analysis. You may see in the next exam, next quiz, how to, or asking you to find the molecular formula or empirical formula. Molecular formula or empirical formula. Let's see, that marks the end of empirical formula 3.5. That is the empirical formulas, determination of empirical formulas, determination of molecular formula. Let's shift gears to quantitative analysis, section 3.6, quantitative information from the balanced equation. What this means is interpreting the balanced equation. When we have, let's say you see here, 2 moles of hydrogen gas reacting with 1 mole, even though you don't see it here, 1 mole of oxygen gas to produce 2 moles of H2O. This is the balanced equation. Those ratio is what the coefficient in the balanced equation is simply what we call the mole ratio. So if I have 2 gas plus 1, even though you don't see that, gas to produce 2 moles of liquid H2O. 2, we read this as 2 to 1 to 2, and of course this is what we call the mole ratio. We call this mole ratio, which we can use to find. It just tells us the mole ratio, not the grams. You cannot say 2 grams react with 1 gram to produce 2 grams. It's only the mole ratio, which we can use in what? In determining how much of each reactant can be consumed or product can be produced. They are the coefficient in the balanced equation. You see now, if you don't master the concept of balancing the equation, you will move forward with the quantitative information you will get from what? The balance. Even the next section 3.7 on the limiting reagent. So it's just the relative amount of moles, which we can convert into what? Into mass of each reactant or moles. So if you see here, this is just a roadmap of what? Roadmap on how to convert mass to mass. By the way, there are, look at this, stoichiometric or types of stoichiometric, here types of stoichiometric calculation. There are mole to mole. We call this mole to what? To mole calculation. There is mole to mass. We can be mass to mole. All right. And then here there is mass to mass. That means you are starting from the mass of the reagent and you are asked to find the mass of a particular product. We call mass to mass. And what I see here is the third type of stoichiometric calculation, that is mass to mass. That means you are starting with mass of A and you are asked to find the mass of B. This is the longest. The third one here, mass to mass. All right. I'll have other resources to show you how to proceed with mole to mass or mole to mass or mass to mole or mass to mole. It's the same thing here. Mole to mole is just the coefficient in the balanced equation. So here, It's the roadmap. That means you have to convert the mass of A into moles of A using the molar mass. You may be required to determine its molar mass using the periodic table. Once you know once you determine the moles of A, you will use the coefficient in the balanced equation, and remember how you set the dimensional analysis so that it cancels out, the units cancels out. And then once you get the moles of B, you will use the molar mass or atomic mass of B to find the grams of B, grams of B. So that's mass to mass stoichiometry. So here is grams to moles, which is type 2 of stoichiometric calculation. You are converting either mass to mole. You see here, grams to mole. Gram is mass. I call mass to mole, or mole to mass. It's the same thing. Okay. We will probably practicing with an example will help you out in determining the mass to mass, or determining the mass of a particular reagent, which will react with a particular reagent to produce mass of B. There are a couple of steps here. Here is an example of glucose reacting with oxygen. The mole ratio is 1 to 6 to 6 to 1. How many grams of water can be produced from 1 grams of glucose? So we know the grams of glucose. So 1 gram, we need to find the mass or the molar mass of glucose. Sometimes you may be given, but sometimes you have to use the periodic table. If you are given, that's pretty straightforward. So what we are doing here is converting the grams of A, 1 gram of A, which is glucose. This 180 is the atomic or molar mass, molecular weight of glucose, this compound right here. If you use the periodic table, 6 carbon times its atomic mass plus 12 hydrogens times its atomic mass, 6 oxygen times its atomic mass, you add up, give you 180. That is the molar mass of A, molar mass of, and then this will give us the moles of glucose in 1 gram. Now we are now adding the mole ratio. This is the conversion factor to change from moles of what? Glucose to moles of H2O. The mole ratio here, this is from the balanced equation. Glucose to H2O, it is 1, you don't see it here, to 6. 1 to 6, therefore, you see the 6 here. If you don't practice with this, you will get confused which one goes at the top, which one goes at the bottom. You may have the numbers, but if you flip it, it's not going to work. And then lastly here, there is a typo here. Please correct that. This should be 1 mole of H2O weighs 18.0 grams, not 180. So fix that. I just want to bring to your attention that we need to put 18.0, and right here is the grams of H2O. What I find it, involving 2 or 3 conversion factors is the mass to mass. It's the longest, I call the longest in terms of what? In terms of the 3 types of calculation. We will look at the heat component in balanced equation or in stoichiometry. I'll leave that to chapter 5 when we get to when we get to the thermochemistry. Thermochemistry, we look at the heat, we will look at the heat. So that is what I want to go through in the stoichiometry. I'll post resources on how you will proceed with mole to mole. It's the easiest. I know you have done that unless you watch the link which I will provide on campus, unless you solve the problems in the homework, use the resources given in there, you won't be able to. This is just, I would say 10% of what you need to know. What I went through in that one example, it doesn't even pass the message because of time factor. I will share with you more resources on mass to mass, mode to mode. Please make sure you watch that. Let's look at the last section here, which is what which is the limiting and excess reagent. But before we do that, let's see. I want you to take note of these three types of calculation. We'll come back to that, and we see how to calculate mole to mass. A limiting reagent, all right, limits the amount of product. It does not mean that something you have in small amount is always going to be the limiting reagent. I'll say this as limiting reactant, all right, that produce less amount of what? Less amount of desired product, less amount of the desired product. So you have to do the calculation and see which one gives you less amount of the desired product. Maybe when we get to example, you will see how this is determined. An example, let me use an analogy here to show you how you figure it out, the limiting reactant. I am not a good artist, but here is here is a bicycle. I don't know how to draw a bicycle. All right. I don't know how to draw a bicycle. Assuming that this is the bicycle, all right? That's a bicycle. It's bicycle. This is here, pi for 2, all right? My bike, all right. Suppose I have, or we have 20 frames and 20 wheels. How many bikes will we assemble? We are in a factory, we are assembling a bike. We have 20 frames and 20 wheels. You will notice that for every one bike, we need two wheels. So we will run out of wheels. That means we can assemble 10 bikes, right? There will be a leftover of the frames. We have excess of frames. So if this was a chemical reaction, we say that the wheels will be the limiting reagent, frames. Excess what? Excess reagent or reactant. And then there will be 10 left, all right? 10 left. Some problem on this section will ask you, what is the limiting reagent? And then you have to figure out which one will give you less amount of the desired product. In this case, if we use all the 20 frames, that means we'll end up with 20 bicycles. And we have to source for extra what? Wheels. So that's an excess reagent, So a reactant which gives us less amount of the desired product is what? Is the limiting reagent. It runs out in a chemical reaction before the other one is exhausted. I like using the one, produce less amount of the desired product. We'll see later on how that is used in calculation. So you can look at this illustration in the text, how H2O is produced. from the reaction between nitrogen gas and hydrogen gas and count how many there are in there. The limiting reagent is used in all stoichiometric calculations to determine the amount of the product. And remember what I said, the one which gives you less amount is called the limiting reagent. All right. Here is an example on how to determine the limiting reagent. So if I have look at that. When 2 grams, 2.00, and there is a reason why you are given 2.00. Why not 2.00000? Why not 2 alone? 2.003 significant figures, which means our answer should be in 3 significant figures. Here is 2.50. Why 2.50, not 2.5 or not 2.500, to stress the fact that all the answers should be in 3 significant figures, okay? Now, given a problem like this, 2 grams of zinc metal in aqueous solution containing 2.5 grams of silver nitrate, the reaction is given by this. Note that when there is nothing in front, it's understood to be 1. 2, we call these numbers 1, 2, 2, 1 here, coefficient in the balanced equation, and mole ratio, I would say, in that equation is 1 to, let's say, here is 1 to 2 to, note that I don't add or I don't use an arrow. You don't use an arrow whenever you are writing. These are the mole ratio, and it represents for zinc, all right, silver nitrate, all right, for silver, and this one is for zinc nitrate. This is zinc nitrate, okay? Those are the mole ratio. The point here is, behind the scene, you need to have that in your mind. What or which reactant is the limiting reagent? At the outset, you need to have, by the way here, you need to have the molar masses or atomic masses of all your compounds. So if I have that, zinc, let me see, zinc atomic mass for zinc is 65.39 grams per mole. We need to know that this is of the periodic table. Zinc nitrate, can I find that? Silver nitrate, we'll find that. .87 grams per mole, 168 grams per mole. All right. Now, zinc nitrate is 189. This is 189.36 grams. Just to give you, I'm looking at the molar mass of each one of them. Maybe I should have this. I wanted you to see that. All right. So that is the mass, atomic mass of our carbon. So we're gonna have that zinc nitrate. And then silver is 107.87 grams per mole. So we need that. In order to find the limiting reagent, say if zinc is limiting reagent, that what we need to do is take the given mass 2.00 grams using the molar mass of zinc. This is atomic mass of zinc 39 grams of zinc, 1 mole of zinc times 2 moles of silver here times the atomic mass of zinc, 1 mole of silver, sorry, Ag 107.87 grams of Ag. This is the atomic mass of silver. Atomic mass of silver. And from the calculation, we end up with 0.6, 6.0, 6.60 grams of silver. If all the 2 grams of zinc metal is consumed, and then we say if the second reagent, Ag silver nitrate, is the limiting reagent, we assume all the 250, because this not 200, but 2.50 grams of silver nitrate consumed using the its molar mass as a conversion factor. All right, we use 169.87 grams of silver nitrate. I'm using the molar mass of silver nitrate to find how many moles I have in 2.50 grams. And again, you should be able to translate the words to chemical formulas. Otherwise, you'll miss it. So 1 mole of silver nitrate, mole ratio between silver nitrate and silver. For every 2 moles of silver nitrate, 2 moles of what? Silver are produced using the molar mass or atomic mass of silver 107.87. 1 mole of silver. So that we end up with that. This will give us 1.5 9 grams of silver. If I compare the two now, 6.60 grams of silver and 1.59 grams, clearly this is the smallest. Therefore, AgNO3 is the limiting reactant. The limiting reactant. That's how you find the limiting reactant. So A is taken care of. That's what you need to know. You assume one is the limiting reagent, how much will be what will be produced. So once I do that, I should be able to compare the two values. And the one with less number of the desired product, less amount of the desired product is the limiting reagent. And of course, B is here. 1.5 grams of silver will be produced from. One thing I want to bring to your attention is the amount, note, the amount expected produced from limiting reagent for theoretical theoretical yield, the amount you expect to get from the limiting reagent is called the theoretical yield. And amount from experiment actual yield or theoretical yield. This is something we will need in determining the percent yield. We're gonna come back to that later on. Just to give you, since we are here, how many grams of silver are produced, that is the theoretical yield. 1.59 is the theoretical yield. So we know zinc strip, the strip of zinc metal is the excess reagent. C is how many grams of zinc nitrate are formed. So in this case, if you look at the limiting reagent and the product in question, the mole ratio is 2 to 1, 2 to 1. That's what we need to, that's what we need to focus on in order to answer question or part C of the problem. So I have C there. What I need to do now is, since this is the limiting reagent, zinc sulfate, silver nitrate, 2.50 grams of silver nitrate times the molar mass of silver nitrate is 169.87. This is from the periodic table. You have to use the atomic masses. You gotta be careful. Sometimes you can Google out what is the mass or atomic mass, molar mass of AgNO3. But unfortunately, in the exam, you have to use the periodic table to find the molar mass if you are not given. So that's where the 169.87 came from. Mole of silver nitrate HNO3 times here 1 mole of zinc nitrate. All right, 1 mole of 2 moles of silver. For every 2 moles of silver nitrate, AgNO3 here, this will cancel out. And then the last one here, the last conversion factor, here multiplying by the last conversion factor, that 1 mole of zinc nitrate, and there is a parenthesis here for nitrate here, zinc nitrate to there, so that 189.36 grams of silver zinc nitrate. This atomic mass is, and that will cancel. We are left with grams of zinc nitrate, and it turns out to be 1.39 grams of zinc nitrate. Like that. 1.39 grams of zinc nitrate. Okay, that's what you need to look at. Remember, we are using the limiting reagent now, because once the limiting reagent is consumed, the reaction will freeze. Nothing will be produced, no reaction will move forward. Therefore, we are using the limiting reagent to find out how much of that product. Please pay attention to the mole ratio. Sometimes the question, some questions could be unbalanced, so you need to balance out fast before you do it, before you proceed with the determination of the limiting reagent. The question will be straightforward, that this is unbalanced unbalanced equation. So you need to balance fast before you proceed with the question on the limiting reactant. Let's see the last part, which is D here. All right, I'm gonna have D here. So how many grams of excess reagent are left? What we know is zinc is excess reagent. Zinc is excess reagent, and we have 2.00 grams to start with. So something will be left over. Not all 2 grams will be used. So how are we going to determine the leftover? We will see the mole ratio or use the mole ratio between silver nitrate and zinc to figure it out how many grams of zinc will react with all the number of moles of the limiting reagent. So at the outset, this is how you will start off with, because this is our limiting reagent, silver nitrate. Let's find the number of moles using its molar mass. This is 169.87 grams of silver nitrate, AgNO3. It's 1 mole of silver nitrate, AgNO3. Up to this point, we have just converted 2.50 grams. All right, 2.5 grams of silver nitrate. To moles of silver nitrate. Let's now, since we are looking at the excess reagent, we want to have or cancel out moles of silver nitrate. We want to find moles of zinc. From the balanced equation, for every 1 mole of zinc that is consumed, 2 moles of zinc, no, I mean silver nitrate are consumed. So that is will cancel out, that will cancel out. We have moles of zinc that will react with the moles of silver nitrate in 2.5 grams. We need to use the atomic mass of zinc to find how many grams will be consumed. So for everyone, this is just the molar mass of zinc. The atomic mass is 65.39 grams of zinc. That will cancel, all right? That will give us the mass of zinc that will be consumed, 0.48. This is consumed, not what will remain. Consumed. Because we're starting, we want to know how many moles of zinc will be consumed from the excess when all the 2.5 grams of the limiting reagent are consumed. That's what the setup on the whiteboard is all about. So if we know what was consumed and if we know what's starting from, all we have to do is therefore excess zinc like that is given by 2.00 grams of zinc minus 0.48 grams of zinc. And we have 1.5 2 grams of zinc. This is excess. This is excess. So you have to see how you rearrange the equation here with the proper conversion factors to find how much was consumed, and then you subtract from. You may have another approach, but the difference is the same. All right, that marks the end of the limiting reagent and excess reagent. Later on, earlier on, I explained to you what theoretical yield is all about. It is the amount expected to be produced from the limiting reagent. Theoretical yield is the maximum amount of the product that can be, not the actual, It is the possible, this is from the calculation, not the obtain, which of course, the other one is the actual yield. This is the experimental, and that is what we will need to find the percent yield. Percent yield, everybody knows this equation. Once you know the actual yield from the experiment, plug it in the equation with the theoretical yield is obtained from the limiting reagent, all right? I have it on the whiteboard that the theoretical yield, the amount expected to produce from the limiting reagent. Let's see here if we can find, before we wrap up, how to find the percent yield, all right? You have to know what is what. Imagine you are working on ways to improve the process by which iron containing iron 3 oxide, this is iron 3 oxide, is converted into iron. So the question is, we are getting iron from iron 3. This is iron 3 producing iron. If, all right, given the balanced equation 1 to 3 to 2 to 3, if you start with 150 grams of iron 3 oxide as the limiting reagent, so we already know the limiting reagent. What is the theoretical yield of iron, theoretical yield of iron? At the outset, we need to find atomic mass of iron from the periodic table. 55 atomic mass of iron, 845 grams per mole. Use the periodic table for iron 3 oxide. Its atomic mass is 159.69 grams per mole. We don't need to find the limiting reagent. We know the limiting reagent, it's iron 3. So we need to know how many grams do we expect from 150 grams of iron 3 oxide. Can I use the conversion factor here? This is the atomic mass, 159.69 grams per mole. 1 mole of what? 1 mole of iron. Oxide. Up to this point, I've just converted what? Converted 150 grams of iron 3 to moles of iron 3. We are relating the iron to iron 3. So here, the mole ratio for mole of iron 3 oxide, mole of iron. If you look at what I'm looking at here, it is 1 to 2. So for every 2 moles, 1 mole of iron 3 oxide consumed. So that when I cancel out this, I'm left with moles of iron. But I need to know the grams. So the last conversion factor here is from the atomic mass of iron. 1 mole of iron weighs 55.845 grams of iron. Just iron. So grams, moles of iron goes with moles of iron. And here the grams of iron is 104. Should double check this, grams of iron. This is how much we expect from the limiting reagent. This is called theoretical. Theoretical yield is 104.9 grams of iron. This is the theoretical yield from the limiting reagent. B, percent yield, and you should know this equation. Percent yield, sometimes we abbreviate this. Percent yield is given by actual yield over theoretical yield times 100. times 100%. So this is the actual. If you are actual, sometimes terms such as this was produced, or use critical thinking skill here. 87.9 grams of iron was produced, and the theoretical yield is 104.9 grams. So iron times 100%. This will be what? Remember, there is either we have what, 180, this is 8. I'll use 84 percent, 84%. Why I'm doing 84 is because of two significant figures here. All right, the zero does not count, but sometimes you may see 83.2. You can just look at that. So it's around 84% from the theoretical yield. Do more problems on the limiting reagent, excess reagent, and how to use those to find the percent yield. You see percent yield for those who are taking the lab, or if you took the lab before, you can remember there were a couple of experiments. There will be a couple of experiments you will be required to calculate the theoretical yield or percent yield of your product. I want to end up part B of the experiment. Please complete chapter 3 homework assignment in MyLab and mastering before it's too late. It's going to be available. I'm just going to send out an announcement regarding the due date as a reminder for those who are yet to catch up with the reading. Thank you.